All right, so the next example, solve the following IVP, initial value problem. Dy to dx equals minus 2x minus y divided by x minus 1 with the initial condition y of 0 equals 1. Now, if we want to figure out whether this is an exact equation or no, we have to figure out what m and what n are in this problem. So if I multiply both sides with x minus 1 here, then I'll get x minus 1 times dy to dx equals minus 2x minus 2y and minus 2x minus y. And if I take the term on the right hand side to the left hand side, then I'll get 2x plus y plus x minus 1 dy to dx equals 0. So this is basically my m and this is my n. Now dm to dy, here it's 1, which is same as dn to dx. dm to dy and dn to dx are both 1. So that means the equation is exact. Now here we have m equals df to dx. And that means 2x plus y is equal to df to dx. Now if we integrate respect to x, so if you remember, the starting point is this. Once you verify that the equation is exact, then the first step you have to do after that is to start with this equation, m equals df to dx, and then you can integrate both sides respect to x. Integrate both sides respect to x. Then we'll have x squared plus xy equals f of x and y plus the constant of y plus a function of y plus c of y equals f of x and y. And then to find c of y, we can use the other condition, use n equals df to dy, and then we will have n, which is x minus 1, equals d to dy of this expression. So d to dy of x squared plus xy plus c of y. Now, derivative of x squared respect to y is 0. So then I can say that x minus 1 equals x plus c prime of y. And that gives me c prime of y equals minus 1. And then c of y will be minus y plus d, where d is a constant. So we can say that the solution of IVP above will be of the form f of x and y equals 0, because again, we have included a constant already here, so we don't need to include another constant in the right-hand side. And then I'll have f of x and y here, and I already found c of y as minus y plus a constant. So then the solution will be x squared plus xy minus y plus d equals 0. And d here is a constant. And now we can find d using the initial condition, like the previous example. Now find d using y of 0. Y of 0 was 1. Y of 0 is 1. Then we'll have 0 squared plus 0 times y minus 1 plus d equals 0. Then d will be 1. So the solution will be x squared plus xy minus y plus 1 equals 0. This will be the solution for our IVP. And this equation right now is written in an implicit form. Solution in the implicit form. If you remember, I've said before that our preference is to have an explicit form. But if explicit form is not possible, then we can leave answer as implicit form. But this solution can be easily written in an explicit form. So this is in the implicit form. How can we write it in an explicit form? We just need to solve for y, isolate for y and solve for y. Note that this can be written in the explicit form as well. So I just need to factor y. So x, I will have y times x minus 1 equals minus x squared minus 1. And then y will be equal to minus x squared minus 1 divided by x minus 1. So this is the solution with our approach that we interpreted as an exact equation. We verified that the equation given to us was exact, and then we followed the procedure to solve an exact equation. Now, is there any other approach do you think we can take? So this was the equation, other than interpreting as an exact equation. Do you think we can take any other approach or any other solution? So solution 2 for this equation, solution 2. If you write the equation one more time, dy to dx, x minus 1 times dy to dx. Equals minus 2x minus y. Now, we can write this as, if I divide everything by x minus 1, dy to dx equals minus 2x divided by x minus 1 minus y divided by x minus 1. Now, if I take the second term on the right-hand side to the left-hand side, then I'll have dy to dx plus 1 over x minus 1 times y equals minus 2x divided by x minus 1. So this is of the form dy to dx plus p of x times y equals f of x. Where p of x here, p of x is 1 over x minus 1, and f of x is minus 2x divided by x minus 1. So this is a linear first order. Linear first order ODE. And we already know how to solve a linear first order ODE. We need an integrating factor, if you remember. Linear first order ODE, an equation of this type, dy to dx plus p of x times y equals f of x. We need an integrating factor called r of x. How could we find r of x, the integrating factor? We need the integrating factor. Integrating factor r of x will be e to power integral p of x dx. And that's going to be e to power integral 1 over x minus 1 dx, which is e to power ln x minus 1. And this is x minus 1. It's going to be absolute value x minus 1, basically, but you can assume x minus 1 is positive, because even if you include absolute value or plus minus here, ultimately we need one integrating factor. So that's why I just used, I just wrote x minus 1 here rather than absolute value x minus 1. We just need one integrating factor so that we multiply both sides by r of x. And then we write the left-hand side as d to dx of r of x, p of x. So multiply both sides by r of x. Then left-hand side becomes, if you remember, was d to dx of r of x times y. This would be the left-hand side after you multiply both sides by r of x. And right-hand side becomes r of x times f of x. If you look at the lecture notes for regarding linear first order ODE, you'll see that these were the steps that we explained before. First, finding integrating factor by e to power integral p of x dx. Then you will find r of x. And once you have r of x, then left-hand side can be written as d to dx of r of x times y. And right-hand side it can be written as r of x times f of x. Now, r of x times f of x, we have f of x here and we have r of x here. So then we will have d to dx of r of x times y equals x minus 1 times minus 2x divided by x minus 1. And then that means d to dx of r of x times y equals minus 2x. And if we integrate, then we'll have r of x times y equals minus 2x plus a constant c. and y will be equal to minus 2x plus c divided by r of x. R of x is x minus 1. So minus 2x plus c divided by x minus 1. And we just need to find the constant c here. Oh, sorry, the antiderivative when we integrated both sides. This is the antiderivative of left-hand side. Antiderivative of right-hand side becomes antiderivative of minus 2x, which is minus x squared plus c. Minus x squared plus c. And to find c, we can use the initial condition. Y of 0 was 1. So y of 0 will be minus 0 plus c, which is c over minus 1. That's 1. So c will be minus 1. And y will be equal to minus x squared minus 1 over x minus 1. So same as the solution we got in solution 1. Same as solution 1 above. All right, so this example shows that some of the equations can be solved using two different approaches. We could interpret the given equation, the same equation, as an exact equation, or equivalently as a linear first order equation. So depending on how you interpret it, then you need to follow the steps or algorithm to solve that specific type of equation. All right, the next topic is integrating exact equations and integrating factors, or exact equations with integrating factors. So let's look at that scenario. Exact equations with integrating factors. So some equations are not exact, but can be converted into an exact equation once we multiply both sides by an integrating factor, by a proper integrating factor. So this is the idea, that if the given differential equation is not initially exact, but we want to convert it into an exact equation by multiplying by an integrating factor. So some equations, some first order equations, first order ODEs are not exact, but can be converted into an exact equation by multiplying both sides, by multiplying by a proper integrating factor. Now the goal here is to find such an integrating factor. Now, so let's consider. So still the equation that we consider is still of the form, still same as previous form, m plus n dy to dx equals 0. Let's consider the first order ODE of the form m plus n dy to dx equals 0. And assume that this equation is not exact, meaning that because m plus n dy to dx will be exact only if partial derivative of m respect to y is same as partial derivative of n respect to x. So if you have an equation of this form, but partial derivative of m respect to y is not same as partial derivative of n respect to x, then it's not exact. And I assume that this equation is not exact, meaning that partial derivative of m respect to y is not same as partial derivative of n respect to x. And we are looking for an integrating factor of the form u of x and y that converts this into an exact equation. So if I multiply both sides by u, then I'll have u of x and y times m of x and y plus u of x and y times n of x and y dy to dx equals 0. And we require d to dy of um to be same as d to dx of un. So instead of writing, u of x and y times m of x and y, I just write u times m for simplicity and for convenience. But when I write u times m, I mean u of x and y times m of x and y. Similarly for un. Now, if I use the product rule, okay, I can use product rule to expand left-hand side and right-hand side. Is it okay so far? So see, so far we require this condition because we require this new equation to be exact. See, this is the original equation. It's not exact because this is not same as this. But after I'm looking for integrating factor u such that after multiplying by u, it becomes exact. When can I say that after multiplying with u becomes exact? Well, I multiplied both sides by u, I got this. If it's now exact, if it's exact now, then that means partial derivative of this function, which is my new m, respect to y must be the same as partial derivative of this function, which is my new n respect to x. So that's why we require this in order for this equation to become exact. Now I can simplify left-hand side and right-hand side using product rule. Derivative of left-hand side respect to y will be uy times m plus u times my. So u sub y is a notation for partial derivative respect to y. And similarly, m sub y is a notation for partial derivative of m respect to y. And this has to be equal to uxn plus unx. So here, uy is same as du to dy. My is same as dm to dy. Similarly, ux is same as du to dx. And nx is same as dn to dx. So then I can take this term, first term to the right-hand side. Then I'll have uy or u times my So let me keep this term here, take this term to the other side, and take this term to the other side. Then u times my minus u times nx equals uxn minus uym. Then that will be u times my minus nx equals uxn minus uym. And then u will be equal to, so what will be, because remember we were looking for u. But before solving for u, let me consider two different cases for u, two possibilities for u. There are in fact more than two possibilities for u. U could be here a function of x and y, but in the special cases, it could be a function of x or it could be a function of y. So those are simpler cases. And of course, a third possibility or third case would is that it could be a function of both x and y. So for now, because remember, for integrating factor, we always try to find at least one integrating factor that works. If you remember, we just saw a few minutes ago that I said that, we had r of x equals ln absolute value x minus 1. And then we could have e to power ln absolute value x minus 1. We could have x minus 1 itself or minus bracket x minus 1. And I said, it doesn't matter. We need one integrating factor, one integrating factor that works. We don't need to find all integrating factors. As long as we have one reasonable integrating factor that provides the motivation or the goal that we are looking for, then we are good. Right now, we are looking for at least one integrating factor that converts the equation into an exact one. As long as I find one such integrating factor, then I'm good. I don't need to find all integrating factors in the world that converts into the exact equation. Just finding one integrating factor is enough. So two special cases. Now let's consider two special cases for u. Note that we are looking for only one integrating factor that can help us convert equation above into an exact equation. We don't need all such integrating factors. Just finding one of them is enough. So now we can consider case one, where u is a function of x only. Okay, u does not have to be a function of x, but one convenient case, one simple case would happen if u is a function of x only. Then we can say that in that case, uy, which is du to dy, will be 0. And therefore, the equation here, which I can call it star, then equation star will be star above can be written as u prime times my minus nx equals u prime times, u times my minus nx equals u prime times n. Because ux will be u prime. If u is a function of one variable only, and that variable is x, then partial derivative respect to x will be the standard derivative of the function respect to x. So u prime will be u times my minus nx divided by n. And this equation will be separable if my minus nx divided by n is a function of x only. In that case, see, again, this expression here does not have to be a function of x only. But if it is a function of x only, then that's a good news for us, and we can view this equation as a separable equation. If this is a function of x only, this is dy to dx. I can take all u's into one side and all x's into the other side. In that case, we can write this is du to dx equals u times my minus nx divided by n. So then this will be du over u equals my minus nx divided by n dx. And then integrate both sides. To find u, and then u will be equal to e to power integral, because this will be ln u equals this. Again, you could say ln absolute value u, but again, you will see that you can handle plus minus because again, we need only one solution for u. We don't need to find all solutions for u. So e to power integral my minus nx divided by n dx. So this is the integrating factor. If my minus nx divided by n is a function of x only. So this is one possibility. Another possibility is that if u is a function of y only. So case 2, the second possibility, if u equals u of y, then a similar calculation to case 1 above. Case 1 above will lead to u equals e to power integral nx minus my divided by m dy. If nx minus my divided by m is a function of y only. Okay, so again, this expression here, nx minus my divided by m, does not have to be a function of y only. But if it is a function of y only, then we can use this approach here and use this formula to find the integrating factor. So the summary is this. So if you have an equation of this four, see, an equation of this form, m plus n dy to dx equals 0. Previously, we saw that if partial derivative of m respect to y is same as partial derivative of n respect to x, then the equation is called exact, and we can follow the steps to solve an exact equation, to find the solution of an exact equation. But if it's not exact, meaning that this partial derivative is not same as this partial derivative, then you have to look at two expressions. First, look at this expression here. First, look at this expression here. My minus nx divided by n. Look at it. Is it a function of x only? If it's a function of x only, then integrate it, and e to that power will be your integrating factor, meaning that if you multiply both sides of your equation by u, then the equation will be converted into an exact equation. So first, if it's not exact, if you don't have an exact equation, first check this. Is the function of x only? If it is, then follow this procedure. Find integrating factor, multiply both sides by u, you will have an exact equation. But what about if it's not a function of x only? Then look at this expression, nx minus my divided by m. Look at this expression. Is this a function of y only? If it is a function of y only, then integrate it. E to that power will be your integrating factor, meaning that if you multiply both sides of your equation by u, you will have an exact equation. Now, you're probably asking right now that what if this is not a function of x only, and this is also not a function of x only, not a function of y only? Then in that case means the equation is not exact, and we cannot find integrating factor this way. We cannot find integrating factor this way either. And all these possibilities will fail in such a case. And then we have to find another approach, another solution for our differential equation. Because remember, interpreting as an exact equation is just one option. And interpreting as an equation which can be converted into an exact equation is also just one option. If all these fail, we can try other things. For example, we saw in one of the previous examples, we could try interpreting the equation as a linear first order equation. So try other methods if these methods fail. Now we can look at an example here. So here this is m. And let's look at another example. So solve the following ODE. Y squared plus xy plus 1 dy to dx equals 0. So right now this is my m and this is my n. So first we have to verify if you want to interpret as an exact equation or an equation which can be converted into exact equation. First, we have to find out about m and n. And first check whether partial derivative of m respect to y is same as partial derivative of n respect to x. First, we need to check that. First, let's check whether partial derivative of m respect to y is same as partial derivative of n respect to x. So right now, partial derivative of m respect to y is d to dy of y squared, which is 2y. And partial derivative of n respect to x is d to dx of xy plus 1, which is also y. These two are not equal. But what can I say? So my is not same as nx. So that means the equation is not exact. But can I convert it into an exact equation? My and nx are not the same. But then if they're not the same, I can look at my minus nx divided by n. Is this a function of x only? My minus nx divided by n. N is this guy. So then I'll have y divided by xy plus 1. It's not the function of x only. So this also fails. What about the other possibility? Nx minus my divided by m. Is it a function of y only? Nx minus my divided by m. This is y minus 2y divided by m, which is y squared. And this is minus 1 over y. This is a function of y only. Function of y only, that means we are in case 2 above. And what was the integrating factor in case 2? U equals, this was the case 2, u equals e to this power, integral of this expression. E to power u equals u of y equals e to power integral this expression here. This expression is minus y. Minus 1 over y, minus 1 over y, minus 1 over y dy. This is e to power minus ln y. And I already explained before why we don't consider absolute value here, because we are only looking for just one solution or one function u that works okay. We don't necessarily need all functions or all choices for u. So e to power minus ln y. And then this is same as e to power ln 1 over y. E to power ln t is always t. So e to power ln 1 over y will be 1 over y. Now I can multiply both sides by 1 over y. Now that I found the integration factor is 1 over y, I can multiply both sides by 1 over y. And what do I get? If I multiply, this is the equation, multiply both sides with 1 over y. Y squared times 1 over y will be y. The equation was y squared plus, write the equation one more time, xy plus 1 dy to dx equals 0. And I'm multiplying both sides with 1 over y, then I'll get y plus xy plus 1 over y dy to dx equals 0. That will be y plus x over y, and no, sorry, x, y plus y cancels with y, so x plus 1 over y. Dy to dx equals 0. Now this is my new m, this is my new n. What will be dm to dy? Dm to dy will be 1. which is same as dn to dx. See, original m and original n did not satisfy the condition for exact equation, but after multiplying both sides with the integrating factor, the new m and new n satisfy the condition for exact equation because partial derivative of this guy respect to y is same as partial derivative of this guy respect to x. And now this is exact. So I can now follow the procedure for solving an exact equation, which was starting with m equals df to dx. And that means y is equal to df to dx. If I integrate respect to x, integrate both sides respect to x, then I'll have xy plus c of y equals f of x and y. Antiderivative of y is xy respect to x, but then I'll also have a function of y included. The constant will be the function of y because the integrating and differentiating everything is respect to x. Therefore, y is considered as a constant. And to find c of y, use the other condition, which was n equals df to dy. Now n, what was n here? X plus 1 over y. Equals d to dy of f. What is f? xy plus c of y. And derivative of this guy respect to y is x plus c prime of y. Now if I compare, I can say that c prime of y is equal to 1 over y. And therefore c of y will be ln absolute value y plus d. So the solution will be xy plus c of y equals, so the solution will be basically f of x and y equals 0. And f of x and y is xy plus c of y, and c of y I already found it. So it will be xy plus ln absolute value y plus d equals 0. So then I'll have xy plus ln y plus d equals 0, or xy minus ln y, plus ln, well, let me leave it like this, xy plus ln absolute value y plus d equals 0, and d here is a constant. And here we don't need to find the constant d because the initial condition is not given. Remember, we always find the constant using the initial condition. Here, the initial condition is not given, so we don't need to find the constant d. We can just leave it as an arbitrary constant. But one thing that I want you to notice here is that how did we get this solution? We got this solution by multiplying both sides by u, but what was u? It was 1 over y. So we can multiply both sides with 1 over y, or in other words, we can divide both sides by y as long as y is non-zero. So this solution is only valid if y is not 0. So this is the solution of IVP above, or ODE above, if y is not 0. Since we divided both sides by y in order to get this solution or obtain this solution. If y is equal to 0, so we had examples similar to this before, that if an expression is non-zero, then we will handle it separately. If the expression is 0, then we have to handle separately. How can we handle separately? We have to see whether y equals 0 in this case is a solution for our ODE or not. It's very simple. Y equals 0 means constant function 0. Just substitute y with constant function 0 and see whether the equation is satisfied. If it is satisfied, that means y equals 0 is a solution, which in that case, it would mean that we have to add it into the set of solutions, because we already found a set of solutions. D is an arbitrary constant here, so it's infinite set of solutions right now. But then if y equals 0 is a solution, we have to add this to the previous set and introduce it as a part of solutions of this ODE. Now let's see whether this is a solution or no. Now our ODE is our ODE was this one was our ODE, y squared plus xy plus 1 times dy to dx. Y squared plus xy plus 1 times dy to dx equals 0. If y equals 0, then y squared will be 0 and dy to dx will be 0. So that means the equation will be satisfied. So that means y equals 0 is a solution. So that means the final answer, y equals 0, and the other form of the solution, which is xy plus ln absolute value y plus d equals 0. With d being a constant, is a set of all solutions for our ODE. See, our ODE here did not contain an initial value. So our final answer will not be just one function. It will be a set of solutions, basically infinitely many solutions with one constant involved in this type of solution, and y equals 0 had to be considered separately. And we verified that it is also a solution. So overall, this is one solution, and this is one type of solution, or one form of the solution. And together, there will be the set of all solutions for our ODE. All right, let's look at the next example. Example, exercise 1.8.103 from your book. Part A, show that every separable equation y prime equals f of x times g of y can be written as an exact equation. And verify that it is indeed exact. Verify that it is indeed exact. So let's look at the equation that is given to us. The given equation is y prime, which is dy to dx, equals f of x times g of y. So if I divide both sides by, let's say, g of y, let's divide both sides by g of y. Then I'll get f of x, 1 over g of y, dy over dx equals f of x. And if I take this term to the other side, f of x minus 1 over g of y times dy to dx equals 0. Now this is my m and this is my n. In order to verify that the equation is exact, we need to check that the partial derivative of m respect to y is same as partial derivative of n respect to x. Now dm to dy will be d to dy of f of x. M is f of x, d to dy of f of x is 0, and dn to dx will be d to dx of 1 over g of y, which is also 0. So my and nx are both 0, so that means the equation is exact. That means we wrote the given equation as an exact equation. And here, like previous example, when we divide by an expression, we have to make sure that that expression is non-zero. Here we divided both sides by g of y. Again, g of y could be 0, but if g of y is 0, then that means, y is a root of g of y, and we already know that y equals a root of g of y is a solution for our ODE. So if g of y is non-zero, we can divide by g of y, and then we have an exact equation which we can solve it. If g of y is 0, then we cannot divide by g of y, but then y equals root of a g of y is a solution for our ODE. So note that in above, we assumed that g of y is not 0. If g of y is 0, then that means y equals a root of g of y. Say y equals y naught. And y equals y naught will be a solution for our ODE. And y equals y naught is a solution of our ODE because you know, dy to dx is 0, which is same as f of x times g of y. Since g of y naught is 0. If y is equal to y naught, the right-hand side will be 0. Because g of y naught is 0 by assumption. And dy to dx, left-hand side will be also 0. Remember, this is our ODE. Y prime equals f of x times g of y. Right-hand side will be 0. Because g of y naught is 0. Left-hand side will be also 0. Because derivative of a constant function is 0. If y is equal to y naught, it will be a constant function. And derivative of a constant function is 0. So if g of y is non-zero, we can divide both sides by g of y and we will have an exact equation. If g of y is 0, we will have another solution for our ODE, which is the root of g of y. Now let's look at part B of this example. Part B, it says solve y prime equals xy using exact equations. So here again, we can say two cases. Case one, you can see if we said that if g of y is 0, here g of y is y. So if y is 0, then we will have a solution for our ODE. Y equals 0, a solution of this ODE. See above. And case two, if y is not 0, then we can divide both sides by y and divide by y. And what do we get? See, we have dy to dx equals x times y. And if I divide both sides by y, then we get 1 over y times dy to dx equals x. Let's take x to the other side, then I'll have minus x plus 1 over y, dy to dx equals 0. Now this is my m, this is my n, and again dm dm to dy is equal to d to dy of minus x, which is 0, and this is same as dn to dx, which is d to dx of 1 over y. So we have an exact equation. And how do we solve an exact equation? We have to start with, so to solve using this approach, to solve, start with m, which is df to dx. And m here is minus x. Minus x equals df to dx. And now integrate respect to x. And then I'll have minus x squared over 2 plus a function of y, c of y, equals f of x and y. Then we need to find c of y using the other condition, which was n equals df to dy equals d to dy of minus x squared plus c of y. And what was n? N was 1 over y. So 1 over y equals derivative of minus x squared respect to y is 0. equals C prime of Y. So C of Y equals ln absolute value Y plus D. Substitute back. Then we will have the solution will be f of x and y equals 0. And f of x and y is minus x squared over 2 plus ln absolute value y plus d equals 0. So this is the solution for our ODE. Now this solution can be also written in an explicit form. This solution can be written in the explicit form, because right now it's a mixture of x and y equals 0. It's implicit, but I can write it as y equals a function of x. I just need to take the first and third term to the other side. ln absolute value y equals x squared over 2 minus d. And then that means absolute value y equals e to power x squared over 2 minus d, which I can write e to power minus d times e to power x squared over 2. And then y will be equal to plus minus e to power minus d times e to power x squared over 2, which I can call this guy f, plus minus e to power minus d. Let's call it f. So f times e to power x squared over 2. So this is the solution for y, where f here is a positive or negative constant. Because e to power minus t is always positive, exponentials are always positive, plus minus that will be positive or negative. Now, if I combine case 1, which was y equals 0, and case 2, then I can say that the combining case 1 and 2 above, you can say that the final answer will be y equals f times e to power x squared over 2, where f here is an arbitrary constant. Because in case 1, we had y equals 0, which corresponds to f equals 0. If f is 0, y will be 0. And so case 1 corresponds to f being 0, and case 2 corresponds to f being a positive or negative constant. So overall, we can say that the solution is of the form y equals f times e to power x squared over 2, where f is an arbitrary constant, either positive or negative or 0. Okay, guys, so that's all for today. So basically, this was the end of chapter 1, first order ODEs. So next time we'll start second order ODEs. We'll start the chapter for higher order ODEs. So we'll start with second order ODEs, and we'll mostly study second order ODEs, but we'll also look at some simple cases of higher order ODEs as well. Okay, guys, so thank you and see you next time.